Let's look at OpenStax College Physics, Chapter 16, Problem 1. Fish are hung on a spring scale to determine their mass. Most fishermen feel no obligation to truthfully report the mass. Of course they don't. A. What is the force constant of the spring in such a scale if the spring stretches 8 centimeters for 10 kilogram load? B. What is the mass of a fish that stretches the spring 5.5 centimeters? And C. How far apart are the half kilogram marks on the scale? So let's write down our knowns and unknowns. In part A, we know that we have a stretch of 8.00 centimeters for a 10 kilogram load. So the mass is 10 kilograms. In part B, we know that the stretch of the spring is 5.50 centimeters. And in part C, we know that the mass is half a kilogram. So mass is 0.5 kilogram. What we're looking for in part A, it's the spring constant. In part B, we want the mass of the fish. And in part C, we want the x, how far apart. All right, so here we have a diagram. On the left, there is a spring that is in equilibrium. So this is the end of the spring. The length of it is, the relaxed length is that. And then we hang a fish, and the spring will be stretched by this amount. So that distance is x. Now the reason that the spring is stretched is because the weight of the fish pulls down on it. So here is the weight of the fish. And we know that the spring exerts a restoring force that goes in the opposite direction. So this would be the elastic force or the spring force that tries to restore the spring to the original unstretched position. And since the fish is in equilibrium as it hangs there, by Newton's second law, we can say that sum of the forces is 0. If I take up as my positive direction, then the force that points up is the elastic force, so that would be F elastic. The force that points down is the weight, so that's W. Sum of the forces is equal to 0. So I can rewrite these. I know that the elastic force is kx. You might ask, why is it not negative kx? Well, because we already picked the elastic force to be in the opposite direction of the weight. So the negative sign stood for the force going in the opposite direction to the applied force. So when I write this down, I'm going to use the magnitudes, and the directions are going to be according to the positive x direction or positive y direction that I chose. So then I have kx minus mg is equal to 0. And here I'm looking for the spring constant k, so k is just mg divided by x. That would be 10 kilograms times 9.8 meters per second squared divided by 8 times 10 to the negative 2 meters. So when I plug in the numbers, I end up with k being equal to 1.23 times 10 to the third newtons per meter. So I have the spring constant of the spring right here. Now in part B, I'm looking for the mass of the other fish, or the next fish. So now I still start out with Newton's second law, sum of the forces is equal to 0, and then I have kx minus mg equals 0. So, but now I'm solving for the mass because now I know the spring constant. So the mass will be equal to kx divided by g. K is 1.23 times 10 to the third newtons per meter. X is 5.5 times 10 to the negative 2 meters. Divide that by 9.8 meters per second squared. And when I plug in the numbers, I end up with a fish that is 6.88 kilograms in mass. Now in part C, I know the mass, I know the spring constant, and I'm looking for how much the spring scale stretched. So I start again with kx minus mg equals 0, and then x will be mg divided by k. M is 0.5 kilograms, g is 9.8 meters per second squared, k is 1.23 times 10 to the third newtons per meter. So when I plug in these numbers, I end up with 4 times 10 to the negative 3 meters, or 4 millimeters. So for every half a kilogram, the spring scale will stretch by 4 millimeters.